The main research target within blueSPACE focuses on providing novel front-haul technologies supporting future demands of the radio access network. Those technologies rely on the introduction of spatial division multiplexing, increasing aggregated capacity, improving latency, and energy efficiency. Spatial division multiplexing can be achieved either using bundles of fibers or multicore fibers for more compact designs. blueSPACE includes the integration of power over fiber technology. Power over fiber provides power with the following benefits: free of interferences, galvanic isolation, low weight, free of sparks influence, and centralized control. Power over fiber signal can also be used to switch on and off critical elements, enter into sleep mode, or wake up from sleep mode. Power over fiber agent at University Charles III uses data from Mobility Manager to decide if RRH must be on or off. Sleep mode or active mode command is sent to power over fiber agent at Eindhoven University of Technology. If sleep command is received, power amplifier energy is cut off. If an active command is received, power amplifier energy is turned on. This is the power over fiber agent at University Charles III in Madrid. It uses the position calculated by the Mobility Manager and information received via Internet about the system to decide whether to send a sleep or an active command. It also shows the information received from the system. The main system controlled by the power over fiber agent in Madrid is located at the Eindhoven University of Technology. It is formed by a BBU, which generates optical 5G data and also receives and graphs parameters about the signal. The optical signal reception stage, which performs an optoelectronic conversion, amplifies and filters the signal. An auxiliary power over fiber agent to establish communication between Eindhoven and Madrid. An electrical power amplifier that amplifies the BBU's received signal and whose energy is supplied through a power path controller controlled by a power over fiber based RRH. An optical demultiplexer to separate the analog radio over fiber signal from the commands sent by the RRH. A multicore optical fiber to transmit all the signals. An optical multiplexer to mix the analog radio over fiber signal and the commands sent in the same core of the multicore fiber. A central office to generate and send sleep and active commands, a high-power laser with an optical switch to generate and distribute the power over fiber signal, and an external source to supply the electrical power amplifier. In the next demonstration, system's main application will be shown. Mobility Manager running in Madrid will simulate user's position. Using this data, power over fiber agent will decide to turn on or off the RRH. Power over fiber agent running in Eindhoven University of Technology will receive and transmit the instruction. Sleep or active commands will be sent depending on the next criteria. When user is on the left side, a sleep command will be sent. Therefore, the RRH and the electrical power amplifier will turn off. When user is on the right side, an active command will be sent, turning on the RRH and the electrical power amplifier. This is the electrical power amplifier connected between the signal reception and the BBU. This is a more detailed view of the signal reception stage, consisting of 2 photodetectors for the 5G signal and for the local oscillator, 2 power amplifiers, one for each photodetector, a waveguide to filter the 5G signal, and the mixer to move down the carrier frequency. Electrical power amplifier's power consumption is shown on the supplies display. By default, RRH and electrical power amplifier are connected and constellation is visible. When connection is established, information takes some seconds to be refreshed. The user is on the right, so the RRH is active and the power amplifier is on. Therefore, the constellation of the received signal is visible. Now, the user is on the left, so the RRH and the power amplifier are off. Since user is on the left and RRH and power amplifier are off, the constellation is no longer visible. In the next section, a second demo will be shown. It demonstrates two different systems working at the same time and being supplied by two different lasers. The first system is supplied by a 1480 nanometers high power laser configured at 32.5 dBm. The second system is supplied by four 808 nanometers high power lasers. Both systems are connected to the same central office, which allows the user to monitor and control them at the same time. Communication between central office and RRHs will also be shown in this demo. A MATLAB application will be used to control and monitor the states of both devices. The elements of both systems are the following. In the 1480 nanometer system, a 1480 nanometer high power laser, a 15 km optical fiber, a 1-to-4 optical splitter, and a 4-cell array to feed the first RRH. This RRH communicates with the central office using two 10 km single mode fibers and a communications board, which also appears at the central office. The 808 nanometer system is made of 4 808 nanometer high power lasers, 4 different multimode fibers with different lengths, 4 cells located on a heatsink, and another RRH, also able to communicate with the central office through two 10 km single mode fibers and a communications board.